Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 5 of a unit Thermodynamics. So let's begin with today's class. In today's class, first we will discuss about the reversible and irreversible processes. Let's have a look what reversible process is. For a reversible process, we can say that a process that can be retraced back such that both system and surrounding return to their original states with no other changes anywhere else is known as the reversible process. Let's take an example of fusion of the ice, or we can say vaporization of water, so that it can be that matter as well as surrounding both came to original state. Ice is there, initially it was the water in a state of a liquid, it freezes and become an ice, again it moltens and again it becomes a water. So in this situation the system and surrounding both regain its original states. The this kind of processes are known as the reversible processes. A quasi-static process, when I say quasi-static process, we have already discussed that it is the processes which take place very slowly. Yes, isothermal kind of task is known as the quasi-static process. So the quasi-static process need not be reversible, or an ideal gas is allowed to expand at constant temperature. An ideal gas is allowed to expand at constant temperature is in a quasi-static process is a reversible. Now let's look at what irreversible process is. It is the process which cannot be retraced back in the opposite direction in such a way that the system does not pass through the same state as in direct process is known as the irreversible processes. We can say all the spontaneous natural processes are irreversible. Such, let's look at the work done against the friction. It is the situation where when you work against the friction, it develops a heat energy, and there is a loss of energy at certain stage. So when that amount of energy has been lost as a heat, or it has produced a heat energy against that work done, then it means that no no heat can be recovered back, and that amount of energy has been wasted is wasted. So this kind of processes are irreversible processes. Let's take one more case. It's an evaporation of water. It's an evaporation of water is irreversible. Again it is going to change once, and once it is going to change, that energy lost has been lost. Let's take few more questions. It's the combustion reaction of a mixture of petrol and air cannot be reversed, or we can say a leakage of cooking gas from a cylinder diffuses to the entire room, which cannot be brought back into the cylinder. So these are the certain processes which we call as the irreversible processes. Let's work for one of the quick question. It's an among the following the irreversible processes is free expansion of gas. Yes, it could be extension or compression of spring. No, this is reversible. That when you extend or when you compress the spring, it can regain its original shape and size. So this could be considered as a reversible. Motion of an object on perfectly frictionless surface. No, all of the above. No. So this free expansion of the gas is the correct option. So I hope now you understand what actually irreversible and reversible processes is. Why we have discussed this? Because we need to discuss the heat engines, and from this heat engine we need to study a very important aspect of the engines, that is what we call as an Carnot engine, which is considered as an ideal engine. So let's first understand what heat engine is, and when we will switch to the Carnot. So first, heat engine. It is a device which converts heat energy into mechanical work continuously through a cyclic process. And so it is going to convert heat energy to the work with certain cycles. And when we say the essential parts of a heat engine are, first it would be the source from where we are going to take an energy. Second is the sink where we are going to dump the energies. Third is the working substance on which we are working. And fourth is the insulated stand so that a proper temperature differences can be maintained. Let's have a look what their role would be. Source is a material which is kept at a higher temperature and having infinite thermal capacity. When I say infinite thermal capacity, I mean that if I am going to take any amount of energy from the source, nothing would be changed for the source. That means, let's suppose if I say that if I have taken 20 joule, if I have taken 20 joule of energy from the source, it doesn't mean that source will lose that 20 joule. It will lose that 20 joule, but source has an enormous amount of energy that change in 20 joule does not make any difference to the source. I hope this is clear. So from the source, any amount of heat can be given without changing its temperature. I hope you understand this, that you can take any amount of energy and that change does not affect the source. Let's understand what sink is. We can say sink is a material which is kept at a low temperature and it is having the infinite thermal capacity. We will kept a sink at temperature T2, and from the sink any amount of heat can be taken from it, any amount of heat can be taken to it, sorry, without changing its temperature, because this is the place where we are going to dump the energy. So if I'm going to give it an energy of, let's say, 40 joule, it is not going to increase its temperature. I hope this is clear. Generally, we keep source at a T1, which is considered as a higher temperature, and we generally kept the source at temperature T2, which is considered as the lower temperature. Now let's discuss what working substance is. We can say working substance is a material which converts heat energy into the work. And when I say it converts heat energy into the work, it is taken in a cylinder fitted with tight but movable frictionless piston so that it can move up or down. The lower side of the cylinder will be thermally conducting with the surrounding so that it can have an exchange of energies with system to surrounding or from surrounding to the system. Let's discuss the last. It's an insulating stand. It insulates the working substance from the thermal contact with the surroundings, and that is used for performing the adiabatic processes. As you have remembered that what adiabatic processes are, that when we say adiabatic processes, we used to have a processes in which we are going to where adiabatic processes, when I'm going to perform the adiabatic process, we are not going to exchange any amount of energy with the surrounding or from the surrounding. So in this kind of processes, insulating stain would require, and this will play a very critical role. So let's look at the situation that this was the source at temperature T1. This will be the sink at temperature T2, and this is the insulating stand. And with this too, we are going to working on this ideal gas, or that is what we call as a working substance. I hope this is clear. So this is the mechanism how it works. Let's have a look the flow diagram. That this is the heat source, and as it is a heat source, it is at a higher temperature. This is the higher temperature. It has been kept at a temperature T1. This is the heat engine, and that is what we call as a working substance. From the heat source to this, a certain amount of energy is being passed on, and that is what we call as a Q1. This is the Q1 amount of energy has been passed from the heat source to the working substance. Now from that a certain amount, it's a Q2 amount of energy, as you can see this, it's Q2 amount of energy has been passed to the heatsink, while certain work done would be available, and that work done would be equals to Q1 minus Q2. So this situation is something like this, that this is the T1, and this is the source of the engine, and this is at higher temperature. This is the working substance on which work will be available from it. So work will be available, and from T1 I'm going to deliver an amount of energy which is Q1. Now this from Q1 amount of energy, a certain work would be happen, and the remaining energy, that is let we call as a Q2, this Q2 amount of energy would be again given to the sink of the system or sink of the engine. So this is how the basic flow of the heat engine work. So let's say it's a working substance which absorbs certain quantity of heat, which is we call as Q1 from the source, and we have this relation that work done is equals to Q1 minus Q2. So we can say the working substance is taken through a cycle of operations such that at the end of each cycle it comes back to its original state and there is no change in an internal energy. That means dq is equals to dw, because as we can say that there is no change in internal energy, that means its a change in internal energy is zero, and if change in internal energy is zero, that means it's a dq is equals to du plus dw. So all the work is going to convert it to the change in energy. So what we can say, it's a net amount of heat absorbed, that is equals to external work done by the engine. It's a net amount of work done that is equals to the external work done by the engine. I hope this is clear. Is it clear? Great. Now let's define a very important term of an engines. It's an efficiency. When we say efficiency, it means it is the ratio of work done by the engine to the amount of heat absorbed Q1 from the source by the engine. So efficiency could be written as it's a ratio of work done to the Q1. And when I say it's a work done by Q1, it is basically Q1 minus Q2 divided by Q1. And this is equals to Q1 by Q1. It's a 1 minus Q2 by Q1. Or this can be related with the temperature as well, such as efficiency is equals to 1 minus T2 minus T1. So this is the efficiency of an engine. So if I want efficiency is equals to 1, it was the relation that efficiency is equals to 1 minus T2 by T1. If I want efficiency is equals to 1, is possible if T2 is equals to 0. Since absolute 0 is not attainable, even an ideal engine cannot be 100% efficiency. Yes, even an ideal engine cannot have an efficiency which is equals to 100%, because absolute 0 cannot be attainable. So one more probability to have an 100% efficiency is that if Q2 is equals to 0, because efficiency was even this, it's a 1 minus Q2 by Q1. So if this is the situation, and if I said that Q2 will be equals to 0, if it is there, if this can be attained, then this eta is equals to 1. That means efficiency is equals to 1 or 100%. But this is never going to be achieved even for an ideal engine, because Q2 is not equals to 0. This is not possible. So that it is impossible to extract heat from a single body and convert that whole work it into the one, because the work done that was equals to Q1 minus Q2. if I can make if I can make this Q2 as a 0, that means total amount of energy that is available from the source has been converted to the work, and this is simply not possible. So we understand that it is not possible to have engines having an efficiency of 100%, or you cannot design or you cannot develop an engine which can convert a total amount of energy that you have received from the source and that engine can convert that amount of energy to the work done. This is simply not possible. So heat engine can convert an internal energy of a seawater if there is a sink of infinite thermal capacity at temperature which is lower than the temperature of seawater. And this this we take a seawater because it is very near to the 0 Kelvin. Since there is no such sink, a ship cannot use the internal energy of a seawater to operate the engine. I hope this is clear. So now every terms are clear. Everything, yes. What is source? What is sink? What is working substance? How does it work? And what are the temperature references? Great. Let's look at certain quick questions. A heat engine is a device to convert work into heat. No. To convert heat into work. Yes. Increase the efficiency. Don't know. Transfer heat from lower to higher. No. It's a convert heat. It is used to convert heat into the work. Next. Efficiency of heat engine. Efficiency of heat engine is defined as the fraction of total heat supplied to the heat engine which is converted into, yes, its efficiency is equals to work done divided by total heat supplied. It's a work done divided by Q1. So it's a fraction of total heat supplied to the engine which is converted into the work. Yes, this is efficiency. I hope this is clear. Is it clear? Is it? Do you have any doubts? Is there anything? Is there any doubts? No? Great. So ready for the question? Let's have a look. We can say that an engine has efficiency of 60 percentage if the source is at 527 degrees Celsius. Find temperature of sink. So how will we do this? First, what they have provided is the efficiency, which is equals to 60 percentage, which is 60 by 100. Next, they have given the temperature of the source, which is a T1. It's a 527 degrees Celsius, but it is in degrees Celsius. I need to convert this to the Kelvin. It's a 527 plus 273. That means it's a 600 plus 200, which is 800 Kelvin. What I want to find out the temperature of this thing. So this T2 is required. How will I do this? How will I do this? So this is simply the efficiency is equals to 1 minus T2 by T1. And when I say it's a 1 minus T2 by T1, this is equals to 1 minus T2, which is, we don't know, divide by T1, it's an 800, and efficiency is given, which is 60 by 100. So this has been gone. This has been gone. And from this, it is simply the 6 by 10. It is the 6 by 10 is equals to 1 minus T2 by 800. So this is 3 by 5 is equals to 1 minus T2 by 800. From this, it's a T2 by 800 is equals to 1 minus 3 by 5. From this, it's a 2 by 5. This is T2 by 800. Hope this is clear. So this is 5, this is 800, this is 5160. So T2 would be equals to 320 Kelvin. This would be the answer. I hope this is clear. If your options have been given, if your options has been given in degree Celsius, because temperature of the source has been given in the degree Celsius, so it is quite possible that they have given the answer as well in the degree Celsius. Then you need to convert this. It's a 320 minus of 273, and this will give me the 47 degrees Celsius. I hope this is clear. But please don't get tempted by the degree Celsius, that they have given an data in the degree Celsius, they have given an answers in the degree Celsius, then let us use in degree Celsius. No, it cannot be used. This is working on the Kelvin only, absolute temperature. You cannot use degree Celsius directly. First you need to convert them. First you need to convert that degree Celsius to the Kelvin, process it with the formula, and again if required convert them back to the degree Celsius. I hope this is clear. Is it clear? Is it? Are you sure? Are you? Great. Let's work for the same question with additional information. In the previous question, if 600 joule of energy has been taken from the source, find first amount of energy amount of energy given to surrounding, and second, work done achieved per cycle. So what I have been provided is that this 600 joule of energy has been taken from the source. So when this kind of question has arise, I must comfortable and I must remember the situation. I should say complete situation. This is the source temperature T1. This is the working substance, and this is the T2, and from where I am going to have this work done. So when I say this is T1, what I understand is I should receive certain amount of energy Q1 from the source. It would be converted to the work done. It would be converted to the work done, and the rest amount of energy would be delivered to the surrounding. This is Q2. So this Q1 amount of energy would be there, from where certain amount of work done would be there, and rest amount of the energy has been given to the Q2. And when I need to find out work done, it's basically Q1 is equals to work done plus Q2, and from this it's a work done which is equals to Q1 minus of Q2. So let's find out first amount of energy, that is what we call as an Q2 has been given to the surrounding. So we have the relation, it's an efficiency which is equals to work done by Q1, and work done could be given as it's a Q1 minus Q2 divided by Q1. This is equals to 1 minus Q2 by Q1. This is equals to efficiency. From this, it's an efficiency has been given, it's a 60 by 100, that is equals to 1 minus Q2, that is what I look for, divide by Q1, and the Q1 was the 600 joule. So this has gone, and it's a Q2 by 600 is equals to 1 minus 6 by 10. So it is 10 minus 6, it's over 4 by 10, that is equals to Q2 by 600. This has gone, this has gone, and this Q2 can be, it's a Q2 can be written as 64, it's a 240 joule. This is the Q2. I hope this is clear. Is it? Is it clear? This is the Q2 which is equals to 240 joule. Now what else I want the work done to? Its efficiency is equals to work done by Q1. Efficiency 60 by 100, work done Q1 it's a 600, so this is 100 6, and work done is equals to 66, which is 360 joule. I hope this is clear. So this was all the terms that what we can have from this information. I hope this is clear, and even you are landed on the same answers. Have you? Have you? Are you sure? Great. So can we move further? Can we? Great. Now let's discuss about the refrigerators. Yes, this all are the part of the heat engines only. Yes, their working mechanisms is differing by certain a very basic and very fundamental principle. But this all are the parts of the different types of the engine. What we can say is, so let's work for the refrigerator. What we can say is that refrigerator, it is the process, or we can say it's a device which can remove the heat from the colder bodies than their surrounding is called there's refrigeration, and this device is known as the refrigerator. So basically what is the task, or what is the role of the refrigerator is that it is going to cool down certain specific region. How it will make it cool? That it will remove the heat from that specific region to the surrounding, which is at higher temperature. I hope this is clear. So we can say, let's these are the essential parts. These are the essential parts of a refrigerator. They are the source, they are the sink, working substances, and insulating state. So it is the same that we have used in the engine as well. Now let's see how this works. We can say a working substance, it is a cylinder with perfectly non-conducting walls and a perfectly conducting base containing a perfect gas as a working substance, and that is fitted with a non-conducting but frictionless piston. A source of infinite thermal capacity is maintained at constant higher temperature T1. Next is the sink of it. It's a sink of infinite thermal capacity maintained at constant lower temperature T2. And the insulating stand, it is a perfect but non-conducting stand for the cylinder. This is the insulating stand. Now let's work for the let's let's go through the model how this refrigerator works. This is sink, and this sink will be at temperature T2. This is source, and this source will be at temperature T1. This would be at a low temperature body. This is high temperature body. So from low temperature body, you are going to receive a certain amount of energy, and that energy we will call as a Q2. This is the working substance on which we are performing this task. It's a working substance, and we are not having the work, but we are going to work on it, and then we are going to pass on certain amount of energy to the higher temperature. So this is how refrigerator work. Now the situation is that why we are not having a work done, but instead of having a work done, or I should say instead of getting a work done from this process, it is exactly the reverse situation where I am doing the work done. Why this has happened? Why? What is the need of this type of done, that we are not getting a work done, but instead of it we need to do our work on the working substance. So let's suppose what is the situation is, let's understand it very technicality, that this is, let's say, refrigerator, and if this is the refrigerator, let's say it is at minus 5 degrees Celsius, and the region around this refrigerator that we can call as a, let's suppose this is the kitchen, this is what we can call technically as a surrounding of this refrigerator, which is at room temperature approximately 27 degrees Celsius. Yes, what you need to do is you need to take a hot energy from the refrigerator, and you need to dump this hot energy to a kitchen which is already at a higher temperature. I hope you understand that you need to absorb the heat energy from this minus 5 degrees Celsius. You need to absorb all the energies which is hotter, which is having a higher temperature. You need to take it, absorb it, and you need to dump it to this surroundings. I hope this is clear. So now this flow will be very easy if surrounding is at lower temperature. But unfortunately, this is not possible. You cannot keep your kitchen at minus 5 degrees Celsius. I hope you understand this. Your kitchen or your surrounding of the refrigerator would be always at the room temperature. And so that the situation will occur that you need to perform a work instead of you are getting work. I hope this is clear. So do you understand this, what I mean to say? Have you got this? Have you have you got this? Do you understand this exactly, what the situation is? I hope this is clear. Is it clear? Is it? Are you sure? Do you have any doubts? Is there anything? So in this kind of engines, you are not going to get the work done, but you need to work. One more thing, if you have observed the refrigerator cycles, that in the summer situations, what happens is kitchen is at higher temperature. Approximately in certain regions of an India, it reaches to the 40, 45, 47, and hottest place it would be around 50, 51 degrees Celsius in nowadays. So kitchen is at 45 degrees Celsius. A refrigerator takes a very large amount of time to get the things cooled. Why? Because its surrounding is very high temperature, so that it needs to perform a very high amount of work to get it cooled. All the objects that you have placed in the refrigerator. But let's suppose if it is the case of the, let's suppose, a winter region. In those regions the temperature is lower. Even the kitchen is at lower temperature. Sometimes it's a 20 degrees Celsius, or in a very cold regions it would be a 15 or 10 degrees Celsius or 5 degrees Celsius. So in that situation refrigerator works efficiently. This is the basic reason. This is the basic reason behind this. I hope this is clear. So now do you understand how the refrigerator works? It takes a certain amount of energy from the low temperature body, and that we will call as a Q2. We are going to perform a work on it. That is the work done. And I'm going to dump this energy to the high temperature body, which we call as the surrounding. So in a refrigerator, the working substance goes through the following steps. Let's have a look. What we are going to do is that we are going to sudden expansion of the gas from high to low pressure, which will cools it and converts it into a vapor and liquid mixtures. And absorptions of the heat by the cold fluid, absorption of heat by the cold fluid from the region to be cool, it will convert it into the vapor. So heating up of the vapor due to external work done on the system, and we are going to release of heat by the vapor to the surrounding, bringing it to the initial state, and it will complete the cycle. I hope this is clear. Yes, so this is how we will cool down. This is how we will cool down the region within the refrigerator. So here we are not going to define efficiency, but instead of to measure the working, or we can say to measure the effectiveness of this substances of this devices, we have defined one more parameter, and that is what we call as the coefficient of performance. So coefficient of performance of the refrigerator can be given as this is equals to beta, and which is equals to Q2 by W, where Q2 is the heat extracted from the cold reservoir. Q2 is the heat extracted from the cold reservoir, and W is the work done on the system. That is what we call as the refrigerant. So, by the law of conservation of energy, the heat released to the hot reservoir could be given as Q1 is equals to work done by Q2, and so this it's a beta is equals to Q2 by W. From this from this it's a work done which is equals to Q1 minus Q2. So this is the beta, it's a Q2 divided by Q1 minus Q2. I hope this is clear. Is it clear? One more thing is beta could contain any positive value any positive value, again theoretically. And when I say it can contain any positive value, I mean to say cannot have negative value. Yes, beta could not be minus 1, beta could not be minus 2, beta could not be minus zero point 0.5, but it could have any positive value. Again theoretically, when I say practically, it could be always greater than 1. But let's not discuss at this point of time, so that we understand that beta could have beta, it's a coefficient of performance of refrigerator, can have any positive value. You can choose it. Next, in a heat engine, heat cannot be fully converted into work. That is what we have discussed in Q2 equals to 0 and T2 equals to 0. Likewise, in a refrigerator, we cannot work without doing some external work on the system. And that's why the coefficient of performance cannot be infinite. And when I say coefficient of performance cannot be infinite, that means a work done on it cannot be a zero. When I say work done on it cannot be a zero, that means it is not possible that you switch off the refrigerator but it will cool down the gases inside it. So this is simply not possible. It is not possible to cool the room by opening the door of an electric refrigerator, because a refrigerator is going to extract the heat from the low temperature reservoir, and it will transfer it to a high temperature reservoir with the help of the machines. So when we say, or when we open the door of a refrigerator, we are not going to cool the room. Basically we are going to make it more hotter. I hope this is clear. Is it? Because what happens when you open the door, a certain amount of heat energy will get into the refrigerators. Yes, if you are not understanding this, let's look at this. This is the refrigerator, and this is the surrounding of the refrigerator. When you open the door of the refrigerator, a heat energy, basically this is at room temperature. Let's say it's a 300 Kelvin. I have assumed it's a 27 degrees Celsius. And let's say this is at 0 degrees Celsius, then that means it is at 273 K, let's suppose. So when you open the door of refrigerator, and air from this temperature, because it is at higher temperature, will rush to the refrigerator, so that refrigerator is going to accumulate it with a hotter energy, or the airs with higher amount of energy, or air with higher temperature. So now what refrigerator needs to do it, that refrigerator needs to pump out this higher amount of energy to the surrounding with more efficiency, and I mean to say with more energy. So the situation will be, you are not going to make it cool, you are going to make it more hotter when you open the door. I hope this is clear. Is it clear? Are you sure? Great. So the coefficient of performance of a refrigerator, it's a coefficient of performance of a refrigerator cannot be blank. It means work can never be zero. It could not be. It could not be ever infinite. I hope this is clear. Is it clear? Is it great? Let's work on the question. Find out coefficient of performance for a refrigerator which can extract heat from the what we can say is the from 5 degrees Celsius, and pass on this heat to the 35 degrees Celsius surrounding So how will you do this? Basically the relation is this. This was the flow diagram, that this was the higher temperature T1, this is the working substance, and this was the T2. T2 has a lower temperature. So what refrigerator does is that it will absorb certain amount of energy from T2 and give it to the working substance, perform certain work on this, and deliver that energy to the surrounding. This will be the workflow. So from this it's a Q2 plus work done is equals to Q1, and from this it's a beta is array sorry work done is equals to Q1 minus Q2, and from beta it's a Q2 divided by W, and when I say Q2 by W, it's a T2 divided by W, or I should say it's a T2 divided by, this is T1 minus of T2, this is beta. So let's put up the value and get it done. It's a beta which is equals to T2 divided by T1 minus T2. Now T2 is at lower temperature and T1 is at higher temperature. So what I have been given is that T2 it's a 5 degrees Celsius. I need to convert this. I need to convert this to the Kelvin. How will I convert it? It is basically a 273 plus 5. That means it's a 278 Kelvin. And the T1 that has been given is 35 degrees Celsius. So this is 273 plus 35, which is equals to 3 plus 5 8, 7 plus 3 0 plus 1, it's a 308 Kelvin. So this is the situation, and I need to find out this beta. So let's put up the value, and get it done. So what I can have is this is equals to T2, which is equals to 278 Kelvin, divide by this is T1, which is equals to 308 minus of 278. This is simply 278 divided by 308 minus 278, which is equals to 30, and this is simply 278 divided by 30, which will give me approximately 9.2 something, and this is the coefficient of performance of this refrigerator. I hope this is clear. Is it clear? Is it? Shall I keep on moving with adding some data? Let's have a look. That in the previous question, in the previous question, if 80 joule of heat has been absorbed from the lower temperature, find out work done, and amount of energy, find out work done and amount of energy transferred to the surrounding. So what will be the situation? Basically it's an 80 joule of heat has been absorbed from the lower temperature. That means you have been provided with Q2, which is equals to 8080 joule, and we need to find out the work done as well as amount of energy transferred to the surrounding. That means we want an Q1. So we have the relation, it's a beta which is equals to, beta is equals to Q2 divided by W. A beta is a 9.2, Q2 it's an 80 joule, this is divided by work done. So from this work done it's equals to 80 divided by 9.2, it's a 92 into 10. Yes. So when I say it's an 800, divided by 92, this is approximately equals to 8.6 joule. This is the work done. It's an 800 divided by 92, which is approximately equals to 8.6 joule. Now I want to find out, I already done this task and I need to find out the Q1. Let's have a look what Q1 is. So it's a beta which is equals to Q2 divided by Q1 minus Q2, and this beta, it's a 9.2, which is 92 by 10. This Q2 was given, it's an 80. Q1 we don't know, Q2 is given, it's an 80. Yes. So from this it's how will I do this? It's a Q1 minus of 80, that is equals to 92 by 10 multiplied by 80. So this is 10 it's a 80, and from this it's a 92 into 8, which is equals to 736 plus 80. It is basically the 736 plus 80, which is equals to 6 plus 3 plus 8 1 plus 1. It's a 1 plus 7 8. So this is 816. This much amount of energy, this much joule, this much amount of energy has been delivered to the surrounding by the refrigerator, so that the things which has been kept within the refrigerator can be cooled down. I hope this is clear. Is it clear? Is it? Are you sure? Are you sure? Do you have any doubts? Is there anything? Are you sure? Great. Now, as we have the heat engine that we can call as a refrigerator, we have one more device which we can call as the heat pump. So what is the working principle? What is the working principle of refrigerator? What do you think? How does it work? So that we understand that refrigerator is used to make a certain specific region as a cooler one. Yes. So how the heat pump will work? Please keep in mind that heat engine and heat pump, these two are the different devices. Yes, heat pump and heat engine, these two are the different devices. We can say that a heat pump is a device which is used to heat up certain regions of system. So basically this is a room heater. You can understand it for the sake of understanding that this is basically a room heaters which we kept installed at our rooms in situation where there are certain regions of India which are very colder one. If you visit the Leh Ladakh, temperature most of the time of the year it is in near to 0 to 10, or it is less than 0 degree Celsius. So you will find there that those people will install a room heaters, even their beds having the heaters, they are the bed heaters. So this all are the heat pumps. What is its task? Its task is as simple as that it is going to heat up the certain region of the system. So the situation will be something like this. First understand the situation, and then we will see the how the flow will be. So the situation will be that, let's suppose this is the specific room. You want to make this temperature of this room as an higher. Yes, so you have installed a heater over here, and this is what we call as a surrounding. This is the surrounding. This surrounding is, let's say, minus 10 degrees Celsius. And what you want that this room would be having a 5 degrees Celsius, let's say, but it is a positive 5 degrees Celsius. So what you need to do is initially even this room is at minus 10 degrees Celsius, but what you want a 5 degrees Celsius. so that you need to absorb the colder energy, the cold waves, and dump it to the surrounding. I hope this is clear. So situation is similar to the refrigerator. Even in the refrigerator, the thing was, you absorb the hotter amount of energy, you absorb the heat waves and dump it to the region which is at higher temperature. So basically you were absorbing the energies which is at higher temperature, and you are going to dump it to the region which is already at a higher temperature. Even here the situation is the same. You are going to absorb this cold waves and you are going to dump it to the surrounding which is already at colder region. I hope this is clear. So it means you are not going to have a work done. Instead of it, you need to do a work on the system. Do you understand what I mean? That forget about the work done, forget about the getting the work done. Instead of it, you need to perform a work on the system so that this can work efficiently. So let's see the workflow of this. This will be the source, and this is at T1 which is at a higher temperature. This will be the sink, this will be the sink, and this is at lower temperature T2, and this is the working substance. What you are going to do is absorb the energy Q2 over here, perform a work on this, and you are going to have this energy. It's a Q1. I hope this is clear. So this is the situation. This is what we call as a working substance. I hope this is clear. Is it clear? Is it? Is it? Are you sure? So when I say it's a coefficient of performance, when I say it's a coefficient of performance of heat pump, let me denote it by small r, then it is the ratio of the heat supplied to the supplied to the total work done that we have performed on the system. So heat is supplied, it's from hotter region, it's a Q1 divide by W, and this could be given as it's a Q1 divide by Q1 minus Q2, or that could be written as equals to T1 divided by T1 minus T2. This is the coefficient of performance. This is the coefficient of performance of heat pump. I hope this is clear. Is it clear? Is it clear? And what we can say is, this is inverse of the efficiency. This is inverse of efficiency. I hope this is clear. So this R is equals to 1 by N. This is for the coefficient of performance of heat pump, and this is the efficiency of the heat engines. This is the relation between these two. I hope this is clear. Is it clear? Is it? Are you sure? Are you? Do you have any doubts? So please noted this down. Please noted it, and we will do one of the question based on this. Do it quickly. Have you noted it? Have you? Great. Let's work for the question based on this. Find out coefficient of performance of heat pump that works on the what we can say is the minus 10 degrees Celsius to plus 10 degrees Celsius, that works between temperatures. Yes, that works between minus 10 degrees Celsius temperature to 10 degrees Celsius. So this T2, it's a minus of 10, which we can say it's a 273 minus of 10, which is 263 Kelvin. And this T3, it's a 10 degrees Celsius. So it's a 273 plus 10, which is equals to 283 Kelvin. I hope this is clear. So for the coefficient of performance of heat pump, this R is equals to T1 divided by T1 minus T2. And when I do this, it's a T1 divided by T2 minus T2. This is T1. So this is equals to, it's a 283 divided by, it's a 283 minus of T2, which is 263. So this is equals to 283 divided by 20, and because it's a 283 minus 263, and when I do this, it's a 283 divided by 20, which is equals to 14.15. I hope this is clear. Is it clear? Is it? Are you sure? Great. Now let's suppose if I have been asked that if the same setup has been used, if the same setup has been used as heat engine, find out efficiency of heat engines. So what we know is the R is equals to 1 by eta, and from this it's a eta which is equals to 1 by R. So basically this is, our R was, it's a 283 by 20. So according to this, it's a 1 by R, which is equals to 20 by 283. Let's calculate this in a percentage. So this is equals to 20 into 100, which is a 2000, divided by 283. It's just approximately 7%. This is the efficiency if our heat engine is going to work between this two. I hope this is clear. Was it clear? Are you sure? Great. So do you understand all this? It's about heat engine. Have you understood it? Have you understand it? Do you have any doubts, any confusion over this? Is there anything? No? Great. Let's just wind up this session over here. This was all about the heat engines. This was just the initially situations, that what heat engine is, what refrigerator is, what heat pump is. In the next session we are going to discuss the Carnot engine, its working and principle and all that stuff. So please, I request you guys to please revise this thoroughly, and before you tune up to that lecture, please be very comfortable with this. Go through this, have a practice a lot with this kind of questions, because this will help us to get Carnot engine done very smoothly. Even if you observe the previous year asked questions, you will find that at least one question has been asked from this heat engine segments. So please do this. This will help us to crack the examinations very easily. Thank you. Have a good day. Take care.